In the second paragraph, it is given that consider the shown arrangement in which helium gas is enclosed inside a adiabatic vessel, having light piston at its top, which is connected to an ideal spring of a spring constant K as shown, and its value is given. Gas can be heated by a heater shown in the diagram. Cross-sectional area of the piston is this much, and initially when gas temperature was 200 Kelvin, spring was in its natural length, and distance of piston from the bottom of the vessel was L0, that is given 0.3 meter. If gas is heated slowly by a heater so that piston moves slowly by 0.1 meter, then answer the following, and it is given that the atmospheric pressure is to be considered 2 into 10 to the power 5 Pascal. So let's analyze the situation. When the heat is given to the gas, then the piston will start moving slowly upward, and at any time t, let when the piston has moved by a distance x, then the pressure of the gas can be written as P0 plus Kx by A. Because the spring is compressed by distance x, so the force acting on the piston is Kx divided by area A. So this is the pressure of the gas at that time. So let's check what we have to calculate. In question number 9, increase in internal energy of the gas sample in this process. In question number 10, work done by the gas sample. And in question number 11, final temperature of the gas. These three quantities we have to calculate. Since we have found out the pressure, now we intend to calculate the work done. So the work done delta W is P into AdX. Variable is x, and x varies from 0 to 0.1. So if I calculate the pressure by substituting the data, so it comes out to be 10 to the power 5 into 2 plus x. So if I substitute the data here, it comes out to be 10 to the power 5 into 2 plus x into area. The value of area is 8 into 10 to the power minus 3 into dx, and integration x equal to 0 to 0.1. So if I solve this, it comes out to be 164 joule. So the correct answer for question number 10 is option B. Now if we calculate the final temperature of the gas, since the number of moles of the gas are constant, so we can write P0 V0 by T0 is equal to P final V final by T final. So from here we can calculate the value of T final. So it comes out to be PF upon P0 into Vf upon V0 into T0. So if I calculate the ratio of final pressure to initial pressure, so the value of x is equal to 0.1 at the final instant. So if I take the ratio, so it comes out to be 21 by 20. So final volume to initial volume ratio comes out to be 32 by 24, and the T0 initial was 200 Kelvin. So on solving, it comes out to be 280 Kelvin. So the final temperature of the gas is 280 Kelvin. So for question number 11, option A is the correct answer. Now we have to calculate change in the internal energy of the gas sample. So in order to calculate the internal energy of the gas sample delta U, we have to write NCV/dt. So N is P0 V0 upon RT0, that is the number of moles, CV, that is 3R by 2, gas is helium, monoatomic, into dt. So if I calculate the temperature change delta T, that comes out to be 280 minus 200, that is 80 Kelvin. So temperature change is of 80. So if I substitute the data, then it comes out to be 288 joule. So option C is the correct answer. So the correct answer for question number 9 is option C. For question number 10, it is option B. And for question number 11, it is option A. Let's move to question number 12.